Alright, so once you brought in your geometry into your case folder, now it's time to open up the terminal. So in Windows, it will look like this. You need to start up your OpenFOAM environment. So for my version of OpenFOAM here is OpenFOAM 2112. And then if you've already made your run folder, you just need to navigate to that. So I'm going to change directory, and then OpenFOAM. And I'm going to keep pressing tab to autocomplete because there is only one path. And the particular name of this case is tutorial. So T, U, tab to autocomplete tutorial, and enter. Okay, so now that's where we are in the terminal. And so we're ready to run commands like snappyHexMesh. But you may not be able to run this because you will be missing some stuff inside here, some dictionaries. So you will need something like snappyHexMesh dictionary, mesh quality dictionary. I believe you're going to need all of these as well. So let's just restart from the beginning. So let me just remove these. And for now, I will just put these over here and delete everything. So if you started from the tutorial, so let me just open another tab here. So remember that we went to incompressible because we know we're dealing with incompressible fluids. We went to look for simple foam because we're working with the incompressible steady state case, Pitts Daily, because we found that one to be the most desirable in terms of the turbulence model. And we're just going to copy everything over. And what you could do is just take everything here and copy it. But yeah, why not? Let's do that. Let's start beginning to end. So I'm just going to remove everything and just refresh it here. So I just press back like that, but you can press this button to refresh. Copy all these folders, and of course this geometry we already made and brought in, and we're going to go into system. There's some things that we don't need here, so let's see. For example, streamlines here. This seems to be something with this particular tutorial case, and remember, if we don't need it, we can just remove it. So let's remove that. A block mesh dictionary, you don't have to use this because we already made the block mesh in Salome. These you will need though. Control dict, FE seams, FE solution. Every simulation should need these. So you should definitely, at the very least, have these. Then we're going to look at our constants. And remember, we already checked our turbulence properties. It was using K epsilon model. You could ignore all these because this double slash means it's a comment. So this is what it's reading, and it's got K epsilon model. It's turning, the turbulence is on, and it's going to print out the coefficients when we start running our simulation. Okay. So that looks good. Oh, another thing that we should check out is transport properties. Does it? So this here, this is where you'll define your kinematic viscosity nu for your fluid. So here it's 1e negative 5. So this, we need to make sure that this matches what we could find for the kinematic viscosity of water. So let's take a look. So I already opened it up. So we have air here. Let's see, 1e negative 5. That looks like it might be air for negative 30 C. That could have been what the, or maybe negative 40 C. Make sure that your units are meters squared per second, and same with all units in OpenFOAM. It's going to be your base SI units. But we're going to look for the kinematic viscosity here of water, because we've decided we want water flowing through this pipeline. And here we go, kinematic viscosity, and oh, we got feet squared per second. Let's see, can we get meters squared per second? Let's expand this. And dynamic, oh, here we go. Kinematic viscosity meters squared per second, and this is to times 10 to the negative 6. Let's go work with approximately room temperature water. So 1, let's round this to 1 times 10 to the negative 6. Let's just add 6 here. Okay, so now OpenFOAM knows that the fluid that we're working with has this viscosity, so essentially it's water. And then we have some initial conditions here, and we're going to have to modify these because they do not apply to ours. So as you can see, these patches here, inlet, outlet, we have different names, right? Inlet big, inlet small, so on and so forth. And then these are the values that you can assign to them. Here in this case, U is velocity, P here is pressure, and then the rest of these are some properties for turbulence. So you need to define these for water as well. So you just find these later, and we're going to do that. So I just kind of gave you an overview, but let's go back to where we left off, which was, so we input our geometry. They're here in this folder. We're now sitting in the tutorial in the prompt, or in the terminal here. So now we need to combine all of our geometries together. So you'll use the command cat, and then since we're here in tutorial, the case file, the root case file, we're going to actually specify where it could find the geometry. So cat, and then it should be under geometry, STL, and then we're going to put an asterisk here saying, okay, so all files inside of the folder called STL, so all these files inside the folder STL are going to be combined into one file, and we're just going to call it region STL. There you go. And then it's going to print it here in the root case folder because that's where we were. And we got this region STL, and you can check it out using ParaView. So install ParaView, make sure to install ParaView. Oh, you also wouldn't have this file here, and I'll show you how to make that later on. And then what I like to do is I just drag and drop this here, and then I don't have it to set to auto update, so I press apply here, and you can see there's different colors because they're all identified as different patches. But yeah, this is exactly what our geometry looked like, so everything is looking good so far. So now what you're going to want to do is go into your constants folder. You're going to want to create a new folder. This one's going to be called tree surface for triangulated surface. We're going to move this into that. So let's move it one more time into tree surface. And so now we have our region STL inside of tree surface. Okay, next step, we need to bring in that background mesh. So what we're going to do is, let me just show you. So where our terminal is here right now, right? We want it to go look inside geometry and look at this background UNV file, and we want it to create that background mesh. So what we're going to do is ideas. There you go. This command, and I press tab to autocomplete. And then the name of our background mesh is background, but if we typed in background tab, it can't find it because of course it's under the subfolder geometry background. Go. And it's finished. So once you see this underscore kind of blinking again, it's done. And it's gonna have created a new folder called polymesh under our constants folder. So now if we do touch, and then you can name it anything. So like you could just, yeah, let's literally name it anything, and then add .foam at the end. It's gonna create a new file called anything, and since we added the .foam extension to the .foam file, and that means that ParaView will default open this file. And if we look at it, what you can see is in our case folder, we've brought in our background mesh. So this is what our background mesh looks like. And if we go to surface with edges, you can see it's broken up into these little squares. And I can actually show you in ParaView inside. I just split it, and and just apply that. And you can hide the plane like that. Show you that inside it's also still squares. Yes. So that was the significance of creating a volume with our in Salome. So there you go. So if you just wanted to check that everything looks good so far, we don't need this hits daily anymore. So let's see. Next, our next step will be to use snappyHexMesh. And of course, if we try to do that, it's gonna cancel here because we got an error. It says we need snappyHexMesh dictionary here. And so I'm gonna bring that back. And you can, of course, find examples of snappyHexMesh dictionary here in the other tutorial folders. But what I did is kind of compile one together, and we'll go through this together in a second. We're going to need that, and I told this snappyHexMesh dictionary to call back to a different dictionary, and I'll explain to you where that's happening. And so we also need this mesh quality dictionary. There you go. And let me just remove these from here. So we don't need that anymore. So now when we run snappyHexMesh, of course it has all the dictionaries that it needs, so it's going to work. It's great. So let's talk about what's going on inside of the snappyHexMesh dictionary here. So when I open this up, there's 3 steps that's going to happen here. It's going to castellate the mesh, snap, and then add layers. And if you don't want it to do any of these steps, for example, if we don't care about adding layers, we just add false here, right? Or we can just leave it as true. You're going to have this first part here, geometry, and you're going to have the name of your STL. So we called it region STL, and it's going to look for it in tree surface, so make sure it's there. And this will always stay the same, so leave this alone. And then you're going to have this here. So the name on the left here is what you called it originally as the STL file, so this will be the name of the STL file. And then this is the name that you're going to want it to be recognized by an OpenFOAM. So let's say in OpenFOAM, I didn't feel like calling it inlet big. Maybe I felt like it was too long. Let's just call it in 1, maybe for inlet 1. But for simplicity, we're just going to leave it the same. We're going to keep the same notation. And there's many different types of parameters that you can change here, and I won't be able to explain all of them, so I think what's best is for you to go into the documentation, the user guide, and find this. And the forums help a lot too. So, because even I don't know what everything does all the time either. So I look these things up with a user guide. Next thing we'll do is you can look at feature edge refinement, and if I do go into this further, I'll make a separate video. So we're gonna skip over this for now. But what you would do is go into Blender, and you can actually tell it to focus on particular edges of your surface. So that's pretty nice if your geometry is pretty complex. Next is refinement surfaces. So you don't necessarily have to refine all surfaces, but you name your patches and walls here. So make sure that the inlets or where your fluid is going to come in from is called patches, and then of course the walls will be referred to as walls. And in here you can go into the documentation and find out what this means. But essentially, if the number is higher, it's going to be more finely refined, so it's going to be comprised of more squares. So let's say in our pipe, there's a smaller section of pipe. If what we did was separate the STL into, instead of pipe wall, just like pipe wall big, pipe wall small, for the smaller section of pipe, we can maybe refine it further if we feel like it's not high enough resolution. And so you can make sure to copy this. Refinement regions. So what I'm telling it to do is inside of the pipe, so where the fluid is going to flow through, we're telling it to we can increase the cube density there. So let's say inside you want it to be higher and higher resolution. You want to capture more of the flow features. You can increase this number here. Some more parameters. Oh, here's your add layers controls. So we're saying at the edges near the pipe walls. Let me just pull up the picture. And you'll see everything in action here in a second once I run snappyHexMesh dictionary. This is the block mesh. We need to look at the region STL. So let's just pull up pair view one more time. And so the point of this add layers is it's gonna go inside and it's gonna break up these cells that are near the pipe walls into smaller cells, because when you have turbulent flow, it's going to be more pronounced. Like the features here near the edge of the walls are important to capture, so you can actually add these surface layers, and these parameters here will change some of the qualities of that mesh near the edge of the wall. And mesh quality control, so this is where I told it to bring in the mesh quality dictionary, and we also put that into system, mesh quality dictionary. So this is basically controlling the quality of all those cells inside that it's going to make out of the mesh. And there's some things like orthogonality, skewness, volume. If some of these parameters are bad, then what will happen is you will have unphysical results when you run your simulation. So I make sure that the mesh is of high quality. And there's a good way to check the quality later on once we start meshing. And everything else, some advanced features. So once your snappyHexMesh dictionary looks something like this, you should be fine to run. So I stopped it here, but I'm just going to pause, let it run, and I'm going to show you the results. So again, before I do that, snappyHexMesh, or I'm just going to press tab to autocomplete. It's going to run the program. And so it may go on for a while, so I'll pause and get back to you. Oh, one more thing I forgot to mention is before you run that, it's actually very important to check your surface to see if it's good. So what we're going to do here, it's going to clear up this terminal. So there's two commands, surface check, that I want to show you. It's one of them. So we're going to make sure that our surface is valid and waterproof in OpenFOAM itself. So surface check. And under constant tree surface, we have our region STL. And it looks like it gave us an output. So it says surface has no illegal triangles. That's good. And this is a problem here. Surface is not closed, since not all edges are connected to two faces. So I'm going to show you how we're going to try to deal with that. So I think in Salome, our surface was waterproofed, but remember that we got that error saying in Salome saying that it's not going to keep the edges, and I think these faces, they're separate, they're not connected to each other. So we're going to try using surface clean, and I forgot exactly how to use that. So when you type in /help or -help here, it'll show you exactly how to use it. So this is how you use surface clean. You can add any options before. Here's your options, but we're not going to mess with these. What we're going to do is this here. So input is your input file. Okay, so surface clean. So we know exactly what our input file is. Surface clean space. Our input here is under constant tree surface. Region STL. And then we have our length, So since the faces are right next to each other, the length could be really small. Let's just leave it at like maybe a millimeter. And then quality. Quality, I have not been able to understand what it is, but let's just leave it at the same as the length here. And then output, so you gotta name the output file. Let's just call it cleaned STL. And it already finished. It looks like it didn't collapse any triangles. So we might still get a problem, but we can check again. So let's just look at cleaned here. So surface check. Let's look at cleaned STL. And we still have some problems. So I'm going to try to tinker with the parameters and let you know what works. And of course, do the same for your use case. Okay, so I checked it out. I tried surface clean. I realized there's an issue, and so what I did was I did a surface check on the cleaned surface, and we find that if I just drag this file into ParaView, you can check it out, and then I told it to look at the different normals, and we see that this face here actually has a different normal from all the other faces. It's only one. And upon further inspection, I see, yeah, these triangles aren't lined up. So if I go surface with edges, they're not lined up here. So yes, you would see water would leak through there. So that doesn't work. So what we're going to do is go back to Salome. So once you've opened Salome, you're going to want to go over to your Mesh tab, click here on Mesh, and we're going to go back to edit the mesh that we created before, the triangulated STL. So as we saw, these surfaces were not waterproof, and the issue was due to it. Well, I guess I'll show you the issue here. So first, start by clearing your mesh data. Okay, and then we're going to edit here. So again, we're going to choose NetGen 1D 2D parameters, 1D 2D, and then for our hypothesis here, it's important that you choose the same parameters every time. So what we're going to do here, and oh, another trick. Let's go to the geometry since we don't have a mesh here. Let's look at the waterproof geometry. So here we're going to have a total of 4 different triangulated surfaces: the pipe wall, the small inlet face, big inlet face, and the outlet face. Of these, you're always going to want to start by meshing with your smallest piece here, because the rest of the shapes will be determined by that smallest piece, and I'll show you what that means in a second. So here our smallest face is going to be this small inlet, so we want to start off by meshing that. Let's go to the mesh, inlet small, let's edit that, and then what we're going to do is choose NetGen 1D 2D, and let's start from the beginning as if this hypothesis is in here. So I'm just going to delete this, show you from the beginning. Inlet small, edit mesh, NetGen 1D 2D. We don't have any customized hypotheses, so it's going to stay as default. And if this was your smallest piece, inlet small, what we're going to do is assign a set of automatic hypotheses, triangulate. Just use the pre-estimated length here, it's fine. But remember, use the pre-estimated length of your smallest piece. Okay, apply and close, calculate that, and here you go. And you're going to see visually that the rest of them will look different now, and as well as it being fully closed now. We won't see any gaps this time. So now going from the small inlet, it doesn't matter in which order we go here, but next I'll just do the pipe wall. And remember to choose the same parameters here. So if you choose different parameters, what's going to happen is you might not get a waterproofed mesh. So choose those same parameters. There you go. And if we zoom in, remember that this was our trouble spot last time, the connecting face between the small inlet and the pipe hole, and we can see it looks totally watertight, and the ends of these triangles match up. That's great. And let's just make sure to do that check for the rest of all the surfaces. And you'll notice since we started with a small inlet this time, the resulting triangulated STL here is actually a bit finer than it was before. And this is definitely the probably absolute minimum fineness we need in order to get some good waterproof geometry. So next, okay, let's check these other surfaces. Outlet is looking good. And you can actually right click and drag to zoom to rather than scrolling the mouse wheel. And this looks very good as well. So now we have a good triangulated surface here, and we're going to export these. No need to redo the background because we're just going to save that from last time. And let's put that into where we keep our geometry. So mine will be here into geometries. This can be in the tutorial here, mesh. This is where we kept it last time. And we're just going to follow the same exporting process. So STL, geometries, mixing elbow. No, sorry, tutorial here. There you go. And we're just going to override the old ones since we have no need for those old ones anymore. This is our new waterproof geometry. Okay. So now going back into our case folder, we're going to check again if our geometry is waterproofed. So I'm just going to clean up this folder a little bit. Let's just delete these. Bring in the new geometries. Place those old ones, those old STLs. Okay, and we're just going to go through the process one more time. OpenFOAM 2112. Navigate to our current case folder that we're working on. We're going to combine all of them together. All of those triangulated surfaces all into one region, STL. And that's going to show up here. We're going to want to put that back into our tree surface. Okay. Now let's do a check mesh, or rather surface check. And we're going to see if it's waterproof this time. Surface check, constant, tree surface. Sorry. Oh, and I can press up and down to go back to the old one. So I messed up. I forgot to type in region STL here. So that was up and down arrow to get that back. So down, up, up, and we can go back through all the old commands that we've already run. So let's go region. Oops, there we go. And okay, so great. Surface is closed. All I just connected to two faces. And no illegal triangles. But there is one problem. It looks like we have more than one normal orientation, and so I'm going to show you how we can deal with that. And that will be with the command surface orient, I believe it's called. So I'm just going to type in surface orient, press tab. Okay, good. So if it can autocomplete, that means it exists. And that is the name of the command there. but I don't remember exactly what the inputs are, so let's double check. Surface orient, and then we can type in help. So surface orient, and we can add any options, but that won't be necessary. Put in our name of our input file, put in the point, and then put in the name of your desired output name. So what we're going to do here is, the way this works is it will, if your geometry is waterproof, it can actually make sure that all the normals of your faces, or what's considered outside for the face, are consistent with each other. So one of the faces has a bad normal, and since it's waterproof, we can use the surface orient. And all we need to do is specify one point that lies outside of the surface. So let's just do negative 100, 100, 100. And that will definitely be outside the surface. And it will orient all of our normals. So let's try that out. Surface orient. We're going to do our input file, which will be in the constants folder, tree surface. And it was called region STL. We're going to name an outside point, and that'll look like this. So let's just go with negative 10. Negative 10. Negative 10. So this is the XYZ coordinates here. And finally, we have to give it a name, and let's just call it oriented, because it's now correctly oriented. Looks like everything went well. Let's just do a surface check on our new oriented surface. So it looks like it just output it here into the main run folder, because that's where we specified it to. Surface orient, or sorry, surface check. And let's go oriented STL. Surface is closed. All normals seem to be consistent. No illegal triangles. Everything's great. So this is ready now for snappyHexMesh. So one change we got to make before we can finally run snappyHexMesh is in the snappyHexMesh dictionary here. We refer to the geometry as region STL, and that's no longer accurate because we have a new one, new STL region. It's called oriented. So let me just clean up this folder from me testing here. And it went into constant, and then let's add it to tree surface so that we can work with it. And then just change all these to oriented. And it should also be here. This is fine. And that should be the only two changes that we need to make. And if not, snappyHexMesh will tell us that something is wrong. So let's run snappyHexMesh. And when I did test, it did take a while. So what we're actually going to do here is let's run it in parallel. That might help speed up the process. We are going to need something called decompose par dictionary. So what we're going to do is I'm just going to take it from one of my other files here. And here it is. We want to run this command here. But then, of course, it needs that dictionary. So let's add that. And I'll show you exactly what's going on here. So in this one, you are going to want to make sure that your method is either hierarchical or Scotch, and you could read a little bit more about the methods, but there's 3 different kinds, and I'll write it here, add a comment. You either have simple, this one's the easiest, but it won't work for when we're meshing, hierarchical, and lastly it's Scotch. So I won't explain what they do here, but you can look up OpenFOAM decompose par, and it'll explain exactly what these are. And I'm going to do hierarchical. This is just the default value, and you can just go X, Y, Z. Most of the times it should work. It should be fine. What's most important here is number of subdomains. So what I want to do is I want to run snappyHexMesh so that it runs on all cores, by default, it will only run with one core. I have a total of 8 cores on my CPU, 8 physical cores. So I want to divide up the mesh into 8 different subdomains, and then each subdomain is going to have one of my processor cores working towards meshing it. So this won't necessarily speed it up 8 times, but this will sometimes help make it faster. So last time it took 1400 seconds to mesh, so we'll see what the difference is here in the end. So when I tested, it took 1400 seconds. So we'll see how long it takes this time, and that was on a single core. So, and then this N here, what this does is it tells you what directions you want to break it up in. So this we might need to actually tinker with. So let's see. Let's take a look at our STL file. So I'm going to open up ParaView, and I wouldn't be able to click on this here because we don't have it in our polymesh. So we're actually going to have to manually go into the geometry, STL, or sorry, no. What we want to do is constants, polymesh, no, tree surface, and this one. This is the one that we'll be working with. And here it is. So I'm looking at the orientation here. It looks like, if I remember correctly, origin is here on this big face. But what's more important is we want to figure out how we can slice up this fluid domain. So since it would be fairly symmetrical if we just slice it down the half this way, that this red plane is going in. So just like this, if we slice it this way. So we'll slice it 4 ways that way. Actually, yeah, what we could do is slice it 8 ways that way. So it'll be 8 slices just like this. So let's go 8 slices. Let's see how this works out. Because what we want to do is make sure that each slice has at least a fairly similar number of cells. And I'm realizing that the ones on the edges are going to have very low cells in comparison, so maybe there's a better way to do this. Let's see. So we can say slice it into 4 subdomains in the X direction, 2 subdomains in the Y direction, so it's going to slice it down this way twice. So it's going to put one down the middle, there's going to be a left side and a right side. That might work. It's not necessarily even, but I think it'll still speed up the calculation anyway, so let's just stick with 421 here. And once you have that dictionary ready, you're ready to slice up the domain. So you write decompose par. It's going to read from this dictionary. I can close this ParaView now. Decompose it. And if we go into our back here, you'll notice processor 0, 1, 2, 3. These are actually the 0 folders, but for each processor. And this is where it's going to print out all the fields from meshing. If you, for some reason, find an error after you decompose par and you want to remove this and go back to how it was before, all you need to do is rm remove -r and processor, right? Because we're still in our tutorial main folder here. Processor. And then you can just add a star. So all files named processor are going to get deleted. If I refresh here, they're gone. But we're going to decompose par again. And you can't just run snappyHexMesh because it's still going to run it single core here. So if you want to run snappyHexMesh in parallel, MPI run, and then you're going to add number of processors, 8 processors, because we split it up into 8 subdomains. And we are going to want to run it in parallel, so -parallel is the next option. And then you type in the command, snappyHexMesh. Parallel, maybe I spelled it wrong. Or maybe the order in which I put it in is wrong. I think you're supposed to add it here. There you go. And I am just going to pause and the time to beat is 1400 seconds, so let's see if it's faster. And I'll come back when it's ready. Okay, so it looks like snappyHexMesh has finished in 609 seconds. It's good, it shaved off quite a bit of time. And now we need to bring everything back. So let's see, let me open up the run folder. Of course, everything is still broken down into these processor folders. Normally we'd be saying 1, 2, 3, or something along those lines here if we ran single core. So what we need to do is reconstruct the decomposed mesh. So let me just clear up this terminal, and we're going to run the command reconstruct par, and then this is a command on its own. This is if you want to reconstruct a parallelized run from a simulation, but since this is just snappyHexMesh, the meshing portion is reconstruct par mesh. There you go. And it's going to merge all of them back together. I hope this doesn't take too long. It looks like it's pretty fast. And so once this is done, we should be seeing some 1, 2. There is a step 3, so let's wait for that to finish before we move on here. And remember, step 3 in our snappyHexMesh dictionary is the adding layers portion. So it's done. All 3 time will be here. We can click on this now that we have these time folders. And let's see how it turned out. Okay, so what you'll see here is the castellated mesh since we're on time step 1. So this is what it looks like. This is the background mesh, but sorry, not feature edges. We want to look at surface with edges. This is what the background mesh looks like, but all of the extra bits of the background that lie outside the surface has been cut away, so you can kind of see it looks very blocky. We do have the layers here, which looks great. Maybe let's look inside too. So the way we can do that is we can cut it in half using clip here. And let's look at it with edges again. Looks good inside. Okay, let's move on to the next time step. Let's see what it looks like on the surface. So after castellation, which is the first step, we have snapping. So notice how it's not blocky anymore. All those blocks have now been snapped to fit nicely on the surface. And that looks great. And let's just check inside as well. That looks good too. There's some portions that are a bit odd, but this should be good enough. There is some small volume cells, so maybe we could work on that, but for the purposes of this tutorial, I think this is probably fine. And the last thing we're going to want to look at is our layers. Sorry, I believe I referred to the smaller cells as layers earlier. That's actually the refinement level. This will be the layers here. And as you can see, maybe, oh, it's not complete here on this face, so we might need to add some extra there, but I think we might still be able to work with this. Let's check what it looks like inside. And you can see there's very small cells here near the edge to capture more of those turbulent effects. And so we're just going to work with this for now. It seems good enough. One thing we might want to do is check mesh. And we're going to want to add some options here. All geometry, all topology, write all fields, and write sets in the format VTK. failed one mesh check here. We have some concave cells, it looks like. And if there's 3 asterisks here, it means that it's a critical error. When you are working with feature edges, sometimes I notice you get these concave cells. So we told it to consider the implicit feature edges, and so that might be what's making some cells concave. And so we might still be able to work with this mesh, so we will check it out once it's done checking mesh here. We can actually visualize it using pair view. So some of these things, concave cells and small determinant, these are influenced by the mesh quality dictionary. So maybe setting some of these to more stricter values might have avoided this. But again, let's check out. Let's see if it's fine. Open this again. And so now you'll have here the option to look at some of these other things. But let's go to the last time step. I accidentally clicked on this one. I should have clicked on this one. This one would go to our last time step. I can click on it now, because we're concerned with what our final mesh is going to be. So let's not look at these parameters on these other 2 time steps. So here you go, last time step, and I do like to look at it with edges. And let's see. We want to look at things like aspect ratio. So there's, of course, a lot of different ways you can go about finding out whether your mesh is acceptable or not, and these metrics will tell you. Cell zone, and we see most of them are blue. And then let's look inside, see where these. So it looks like this is fine. Another way that you can look at it without having to look for these cells visually is a histogram. So if you go alphabetical here, and you should have one called histogram. There it is. Click apply, and then it will tell you here. So select input array, you can look at skewness, apply that, and it tells you, so this is the skewness value, and this is how many cells fall under that. So the more skew we are, the worse it is. And depending on your use case, you may need more or less skewness. This is still looking fine for a tutorial case, so we're just going to roll with this. And let's just remove, now that we've reconstructed, we have all these time steps together reconstructed here, so we can actually remove these folders to help declutter. So we're looking for rm-r processor and all of those. Let's refresh. So the last step is to copy all the folders inside of your latest time step polymesh folder and bring it into your constant polymesh in here. So what you're going to do is cp copy -r. This is your input, all of your folders from your latest time step polymesh, space, and then the last one here is the constants folder polymesh. Press enter. It's going to copy into there, and then you are done. You can actually remove these time steps, and you are ready to start your simulation once you've set up your initial conditions. So that'll be the next video, and that concludes the meshing video.